In this video, we're going to work through a problem in which we have a gaseous reaction, and our problem setup is that we have 20 moles of gaseous ammonia and 15 moles of oxygen gas. They're going to react to form nitrogen monoxide gas and water vapor. We have our balanced equation here with 4 ammonia, or NH3, in gas form, plus 5 oxygen, yields 4 nitrogen monoxide, NO, as a gas, plus 6 H2O, and that's water vapor, so it's also a gas. So if this reaction occurs at 30 degrees Celsius in atmospheric conditions of pressure, so 1 atm, what will be the final volume of the unreacted component and products? So right away we know there's going to be some of one of the reactants left. We're going to have some unreacted component. So first we need to determine which component that will be, or determine our limiting reactant. So we're going to start by assuming all reactants react to determine which reactant produces less product. So we have 20 moles of NH3 and if we look at our balanced equation, we can see for 4 moles of NH3 we're going to produce 4 moles of NO. So that's going to leave us with 20 moles NO produced. Let's do this again now with our oxygen. So we have 15 moles of O2. And once again, looking at our balanced equation, we see that for every 5 moles O2, we get 4 moles NO. So that's only going to leave us with 12 moles of NO produced. Therefore, oxygens are a limiting reactant. So, limiting reactant, just for a quick recap, is the reactant left over, or the reactant that's completely used up in the reaction, and then other components might be left over because they don't have any more oxygen to react with. So our next step, we're going to determine the number of moles present after the reaction. So to do this, we're going to do a little more stoichiometry. So we have our 15 moles O2, which we know is all reacting. And first, let's find out how much water vapor we're going to produce. So we know 5 moles of O2 will become 6 moles H2O, or we'll do that stoichiometrically. And that's going to give us 18 moles water vapor produced. We already know that we're going to have our 12 moles of NO produced, so which we see above. And now we need to figure out how much of our NH3 is going to react, because not all of it is. So we have 15 moles O2. Now we need to compare this to our NH3. So for 5 moles of O2, we're going to have 4 moles of NH3 react with that. So that's going to tell us that we have 12 moles of NH3 react. So, if we have 12 moles react, we know we start with 20, so we have 20 moles NH3. We're going to subtract off our 12 moles of NH3 to get a final amount of 8 moles NH3 left. And lastly, we need to find out the total number of moles present. So we know we have our 8 moles NH3. To add to that, we're going to have our 18 moles of the H2O, and we're going to have our 12 moles of our NO, which is going to add up to be 38 moles. So now we have to figure out how to come up with a volume based on the fact that we have 38 moles. And what we're going to do is we're going to use the ideal gas law assumption. When we do this, we're going to assume our water vapor, NH3, and NO are going to behave as an ideal gas. So, when we think about our ideal gases, we think of our ideal gas law, which we know is PV equals nRT. And we want our volume, so we're going to solve for volume. That's going to give us V equals nRT divided by our pressure. Next step we're going to have is substitution. So we know all of our components here on the right side of the equation. So we're going to put in our number of moles, which is 38 moles, times our R constant. And remember that R constant is just something you would look up in a table. It's our ideal gas constant. And that's going to be 0.08206 liters atmospheres per mole Kelvin. And we're going to multiply by our temperature, which has to be in Kelvin. So it's going to be our 273.15 plus our 30 degrees Celsius. So that'll give us an answer in Kelvin. And we have to divide all of this by our pressure, which was 1 atmosphere. And that is going to give us an answer of 945.3 liters. So we should probably have a pretty big container to put this all in. So that is how you can go through a gaseous reaction problem to end with solving for the volume of the product.